Hi, it's Mr. Baker here with another physics video. Today we're going to be looking at sound and ultrasound. Okay, so today we're going to be looking at sound and ultrasound, and we're going to be answering this question: what is ultrasound and what can it be used for? So, how do we hear? We hear different sounds of different pitch and different loudnesses. These can be picked up because of how we hear. So first of all, sound waves enter your outer ear and travel through the ear canal to your eardrum. Your eardrum vibrates with the incoming sound and sends the vibrations to three tiny bones in your middle ear. The three tiny bones are the malleus, or the hammer, the incus, or anvil, and the stapes, or stirrup. The bones in your middle ear amplify the sound vibrations and send them to your inner ear, or cochlea. The sound vibrations activate tiny hair cells in the inner ear, which release neurochemical messengers. Your auditory nerve carries this electrical signal to the brain, which translates it into the sounds you can hear. To be able to hear at different frequencies, the different parts of your ear have to vibrate at those frequencies. As you get old, parts of your ear may get damaged because of working conditions or listening to loud music. This means that parts of your ears can't resonate at the same frequencies as they used to, and your hearing range may decrease. Right, let's have a look at a definition that we really need to understand to be able to describe sound in a bit more detail. So what does hertz mean? The unit of frequency is measured in hertz. It measures how often something happens in a second. So 1 hertz equals one thing happening per second. In sound, that would be one sound wave passing a point every second. How do we measure frequency? So we can use an oscilloscope connected to a source of sound, and we can actually see the sounds. A source of sound may be a signal generator or a microphone. The loudness is proportional to the amplitude of the wave. The frequency is another name for the pitch of the wave, the number of waves per second. So a higher pitched wave would have more waves per second. You'd be able to see more waves on the screen per second. And the loudness of the wave would be proportional to the amplitude of the wave. The higher the peak of the wave, the louder the wave. On an oscilloscope, the y-axis measures the voltage and the x-axis measures the time. For the voltage, 0 is straight through that central point there. Above that would be positive and below that would be negative. So I'm going to play you some sounds so you can see the different pitches and so you can see how we can see those different pitches. The accepted frequency range for a young, healthy human is 20 Hz to 20,000 Hz. Ultrasound is a sound that has a higher frequency than our ears can hear. The upper limit decreases with age or exposure to loud sounds. So we've said that our frequency range is between 20 and 20,000 Hz, and anything above 20,000 Hz is what we call ultrasound. A dog can hear 67 to 45,000 Hz. And that's why some people use dog whistles to call dogs that are higher pitched than our ears can hear, or very high pitched noises. And bats have a range of 2,000 to 110,000 Hz. And bats will emit high pitched calls that will reflect off objects, which will enable them to navigate. So one practical application of ultrasound is something called sonar. Sonar means sound navigation and ranging. It uses the principle of echolocation that some animals like bats use. A signal is sent out and the time taken for it to return to its source after reflecting from a surface such as a lake bed is measured. If you know the speed of sound in water, it's then possible to calculate the distance the sound has travelled. So we can use our equation for speed to find this out. So if speed equals distance divided by time, then distance equals speed times time. So if we send a pulse from the boat to the ocean floor, we can time how long it takes to get to the ocean floor and back again. So if we want the time it takes to get to the ocean floor, we can halve this time. If we know how fast the ultrasound travels in water, we can then use the equation to find the distance. So let's have a go at an example. Sonar can be used to detect shoals of fish. A pulse of ultrasound is sent out from the boat and an echo is heard 0.3 seconds later. The speed of ultrasound in water is 1,530 meters per second, so calculate the depth of the shoal of fish. Okay, so we're doing a calculation, so remember DESRA, so D for data, so the total time is 0.3 seconds. Time to the ocean floor equals half the total time, so that would be 0.15 seconds. E for equation, so our equation is distance equals speed times time. So let's substitute in the values. So we've got the speed is 1,530 meters per second. We know the time to the ocean floor is 0.15 seconds. So the distance to the shoal of fish is going to be 1,530 times 0.15. In this case, we don't need to rearrange. And so our answer is going to be 229.5 meters. So the distance to the shoal of fish is 229.5 meters in this case. Okay, so let's have a look at how ultrasound scanners work now then. So here I've got the body tissue that we're looking at. So maybe we're looking at muscle or something like that. And here we've got the skin. This is the outer skin of the body. So first of all then, a thin layer of jelly is placed onto the body, onto the skin, and that makes sure that all of the sound from the transducer enters the body. A transducer is anything that changes electrical signals into another type of energy form. So in this case it would be electricity into sound, into ultrasound. So a pulse of ultrasound is sent out by the transmitter, and you can see that blue arrow there. A pulse is partially reflected from the surface of all the materials with different densities and returns to the receiver. Millions of sound waves are transmitted every second. As the waves reflected at different times, the computer in the ultrasound machine calculates how far the wave travelled before being reflected, using distance equals speed times time. Note the time here is there and back. Using this information, the computer builds up an image of the inside of the patient. So these are the kinds of scans that you might see, two different types of scans, one called an A scan and one called a B scan. In an A scan, the initial signal is reflected as it went through the skin to start. Every time the ultrasound goes through the surface of a material at different density, it partially reflects. These partial reflections can be then used in hospitals to build up a picture, like the scan of a fetus, or by engineers to see flaws in metal objects. Where there are cracks, the ultrasound will reflect, and this can be used to find these imperfections. In an A scan, you'll see the reflections of the pulse of ultrasound. In a B scan, all of these pulses will be built up together to make a picture. So in an A scan then, you can see on the y-axis we've got the signal strength, and on the x-axis we've got the time. So when the ultrasound probe first gives out the ultrasound, some of the sound is reflected off the skin. Then it picks up the reflected signal and we see a pulse there as well. So the time between the initial signal and the reflected signal is the time to the body tissue, the muscle or whatever, and back again. So let's have a look at an example then. So use the ultrasound A scan diagram to find the distance from the skin to the bone in the body. So we have been given some information that the speed of ultrasound through body is 1,540 meters per second. And we've been given the time in milliseconds between the initial signal and the reflected signal. So the reflected time is 0.12 milliseconds. So that means that the time to the bone is going to be half of this time, so it's going to be 0.06 milliseconds. We've got our equation, distance equals speed times time. So distance equals speed, 1,540, times time, 0.00006 milliseconds. So we have a distance of 0.0924 meters. So that's the end of this one. These are the things you should be able to do. You should be able to describe the properties of a sound in terms of loudness and pitch. You should be able to identify the range of frequency that humans can hear. You should be able to measure the frequency of a sound wave using an oscilloscope and know the relationship that frequency equals 1 over the period. You should be able to outline some uses of ultrasound and describe the operation of an ultrasound transducer. You should be able to describe the structure of the human ear in terms of transfer of waves and vibrations, and you should be able to calculate the positions of flaws in metal objects using data from ultrasound traces. So this is what we asked at the beginning. We said, what is ultrasound and what can it be used for? So ultrasound is any sound that is above 20,000 Hertz, and it can be used for scanning things like prenatal scans, or engineers can use it to find imperfections in metal objects by scanning them. Okay, so I've been Mr. Baker. That's been another physics video all about sound and ultrasound, and I'll see you next time. Thanks very much.